Hi everyone, I'm very happy that you are here for the first workshop. My name is Rogier Bos. I'm sorry I forgot to introduce myself earlier. I'm assistant professor here at the University of Utrecht, the Freudenthal Institute. I'm very happy that I can share with you some of the research I do here, which is actually based on realistic mathematics education. And in this sense, I hope that this presentation will show you an example of how to implement ideas that were mentioned by Paul before into secondary school. So the title of my talk, which is supposed to be a workshop, but unfortunately, because of the way it's set up now, being online, it will be a bit more like a presentation, I'm afraid. The title is A Smooth Slope to Slide is a Smooth Slide to Slope. So this is actually grammatically correct, even though it might seem, especially in the end, that it's wrong. But it means that I hope that this lesson will, in the end, be a smooth slide towards the notion of slope. I like to play with words, so the subtitle of this workshop is Slides About Slides. And what you get from that is that I will talk about a slide. And actually, if you've done the preparation task for this workshop, which makes it into a workshop, then you know it's about a slide and you've already designed your own slide. So here's the slide that is actually about me. It involves what I said already, and it tells you a little bit about my background. So I actually was a teacher for about 8 years in secondary school, and that still influenced a lot the way I do my research. I'm really interested in implementation and seeing what my ideas do in the school. Then the plan is as follows. First, it's always important to ask, what's the problem at all? Is there a problem? And then I'll tell you a bit about how we're thinking about solving it. It will be a lot about meaning making. Actually, this is good given Paul's talk, where it was a lot about meaningfulness. And I think Paul sometimes said that realistic maybe should even be replaced by the word meaningful, because that's much more clear about what realistic actually means. Then we're going to talk about what students did on the task. Now, you've worked on the task yourself. You will probably be interested what students, secondary school students, did on this task. Then finally, some questions came up in Paul's talk about about how to guide the students. What does it look like in classroom when you teach according to RME? Well, I hope to address this in this section. Then we'll look a little bit about different ways to talk about slope of a curve from a mathematical point of view. And this is important because somehow you have to relate what students come up with the mathematics as we know it, the whole system of mathematics, the mathematical building. And there turns out to be more approaches to slope than the standard one. And somehow, surprisingly, this is also what students come up with. They do not always come up with the standard approach. And of course, we'll wrap it up and have some conclusions in the end. So what is the problem? The problem is this: how to teach the slope of a curve in a meaningful way. And then one way to make it meaningful is by reinvention, because you then build on what is meaningful for students. So can students actually reinvent the notion of slope of a curve? Well, it's always important to think first, like, where do students come from? And for this task, we have to decide what is the prerequisite knowledge. And I want to ask you to first say, okay, what do you think students need to know about slope before they start? Sorry, what do they need to know before you can start teaching them about slope of a curve? And what are the things that you would like to teach? So please share these things with each other in the comments right now. And that way we'll have a sort of an overview of what you know about the teaching situation that we're going to talk about. Okay, thank you for sharing these things. As you go, I will mention a few things. So it's important, of course, that they know about slope of lines. That's what you learn first. You learn to do the rise over run, delta y over delta x for a line. You need the equation for a line. Y is m times x plus n, or a times x plus b, you sometimes see. So linear equation. Then, of course, you need to know a few curves themselves. Of course, and then we're going to talk about this. There's a lot of pre-knowledge, prerequisite knowledge. They know a lot about steepness already. They know a lot about smoothness already. So we'll get back to that. This is a very nice scheme that was written by Zandier. That's a researcher in mathematics education at some point, and it was a little bit extended by David Roundy and others. And it shows you some aspects ordered on, well, the columns here. There are graphical aspects of it. There are verbal, symbolic, numerical, and physical aspects of slope. And, well, there you go. You see the pictures. You see the notion of average rate of change. And then in a limit, it becomes instantaneous rate of change. So these are aspects of slope that you would like to teach. And you see that there's some sort of transition there going from ratio to limit. There's also a physical aspect, nicely illustrated with pressure and volume. Okay, that was a little bit about what is the problem and what is, what you need to know, what you'd like to teach, what you'd like students to understand. Okay, now the task, and you already know the task, but I'd like to say a little bit why this task. Well, it's motivated from realistic mathematics education, and a common approach here is to introduce a new concept through a task of which the context provides opportunities for students to focus on reasoning and representations related to the notion aimed at. There were questions before about the role of context and what's the difference between realistic and contextual. Well, the point is the context is just the starting point, and it becomes realistic mathematics education if you use the context in a certain way. And here it should trigger certain streams of thought within the students. It should give them opportunities to start reasoning about a certain situation and reasoning towards the mathematics that you're aiming for. So that's the goal. And so the challenge is to try and find such situation. And if you want to build on ideas about slope that are meaningful to students, you have to sort of think about, okay, what situation do I know that might be relevant here? And, well, that relates to what actually is meant by meaningfulness. Well, we just discussed a little bit about that in the previous session, but I have a slightly different approach maybe, which I think comes between the lines. It is in the book by Freudenthal himself. And it's a sort of recursive definition of what meaningfulness is. I think what he says is things are meaningful if you base them on things that are already meaningful. Now, that might seem circular to you, but it is actually recursive because, okay, you can build meaningful things on things that are already meaningful. And the only thing we have to do is what's the primary, what's the first meaningful thing then? And those are the everyday experiences that you have. So you'd like to start from an everyday experience. Those are meaningful to you because you experience them every day. And from there, you'd like to build more and more abstract things that remain meaningful because they're grounded in previous meaningful situations that you have. And this relates to, well, a vision, an idea from a completely different area, namely the cognitive science. And that's the idea of embodied cognition, or grounded cognition, as Barsalou calls it. And that's a wonderful idea, I think. And it says the following: Grounded cognition reflects the assumption that cognition is typically grounded in multiple ways, including simulation, situated action, and on occasion, bodily states. So this sort of first meaningful things, these everyday situations, could be bodily experiences, things that you do, or things that you did before but that you're still capable of simulating in your head, like going down a slide. Everyone has done that multiple times. You can simulate it. You could still imagine what it feels like when it's steep, when it's smooth. You know these things. So what do we get from this? Mathematical cognition on the slope of a curve needs to be grounded in a situated action in simulations or bodily states of experience involving steepness and smoothness. So these two lovely children here are very much enjoying their ride down the slide, and their papa is happy too, because he knows that actually they're already developing these first experiences that they will later mathematize into the derivative. They're experiencing steepness and smoothness. This might seem a bit abstract, but imagine that you would live in a one-dimensional world and you would never experience steepness in your whole life. Then the derivative would be a very abstract notion. You would not be able to use the geometric approach to what a slope of a curve is. So these experiences of going down the slide are important. You can use them. I can already ask my son, show them a slide and ask him, where is it steepest? He'll know, because that's where he experienced it as steepest. I can show him a slide with a bump and ask him what's not nice about this slide, and he'll know he'll know that it's not differentiable at one point. I could teach him that word coming from these experiences. So I hope that this makes the notion of meaningful more meaningful to you. So, but this is not yet a lesson. So we'd like to go to a task and a lesson. So the task is this. Please, you know it already, but I just repeat. Please design for me a slide with a straight bit and with a curved bit, and let them meet in a smooth way. And please not just design it for me, but give me an equation for the straight bit, an equation for the bended bit, and give me the point where they meet. Now you have done this, and I've really enjoyed looking at your solutions. It was interesting because you've chosen many different ways, some more algebraically, going for an exact solution. Others used GeoGebra to sort of fit two things together and got a numerical approach of a solution. And nicely, that reflects probably your different backgrounds as well. And I'm interested in what ways students solve this. I am interested in how you solved it, but also in particular how secondary school students solve this. Because, I can make them do this task, but then I have to use their solutions to build my lesson on. To facilitate them eventually ending up at the notion of derivative in a point, of slope of a curve in a point. So their first solutions may not immediately involve the notion of derivative because they don't know it yet. It will sort of have little informal ideas that I can use and build upon and can help them with. So please, if you have ideas of what your students may do, put them in the comments here just to share among each other and to discuss as I am talking. So let's talk about the task first a little bit from the theoretical point of view. So why do I think this is a good task? Well, we already talked a little bit about minimal pre-knowledge. They need to know about equations for lines and curves, but that's all. And on secondary schools, that's very fortunate because they spend the first 3 years on secondary school a lot on equations for lines, and also on the parabola, for example, or the hyperbola. That's what they learned before. And they learn to solve all sorts of equations with that. So they can really use this knowledge It's very much realistic for them, these sort of things. It's meaningful to them. And then I think this task suits very well two principles, as also discussed by Paul Drivers before, namely the reinvention principle. Based on this task, they can start developing notions of derivative. Why? Because if you want this straight line to meet the curved line, it will have to be a tangent line to the curve. And if you want to choose the right tangent line, you'll have to have the right slope of that line. And as you will see from the students' results that I'll discuss later, they are going to get to this point. But I want to have the line in the right direction and I want to choose this right. And it has to be tangent. They might not use the word tangent, but some will. And a lot of these things will come up. So this is definitely working towards reinvention. And then the other thing, which has already been suggested by many things I said, is the emergent models idea. So you have to be patient. You should definitely not expect students to come up with the limit of delta x goes to 0 of delta y divided by delta x. But of course, that's not what is going to come out of this task. But we're going to have situational models. We're going to have informal models on which we would like to build, which we would like to develop. So what comes out of the task is not the final product of the lesson. So we want to change the models of slope that are still really tied to the situation of the slide into more abstract models for slope. That's the goal of the lesson. All right, just to, this question was also in Paul's talk. They asked, well, give me some examples of how RME was implemented in lessons. Someone asked even for a video. This is really hard with privacy issues, but there are reports and also recent reports. These are people who used reinvention principle and more emergent models principle in recent years in several subjects. I'll share these slides so you can look them. You can look at them in your own time and find these references. It's been used in calculus, it's been used in linear algebra, in abstract algebra, statistics, even bifurcation diagrams for those of you who know what this is. So there's plenty of proof that this can be used in a good way in classroom, and I hope I can add to this proof. Actually, as I'll show on my last slide, we recently had a publication also about this, in which we try to convince you that this is effective. But I also want to convince you now already. So maybe the most convincing is by showing what students do with this task. And there we go. This is one of them. We're just going to show you a selection of interesting things, but it gives you a good idea of the diversity of things. So this is one of the solutions of the students. Very nice. It's a hyperbola. Y is 10 over x. And then there's a line that's a bit hard to read. It says y is minus x plus 6.4. Now, I, of course, tried this at home. Later, I was there in the classroom as well, and put it in GeoGebra, and this is the solution. And it's really interesting because in their drawing it looks all right, and here it still looks all right, but if you look very carefully, you'll see it's wrong. Now, the nice thing is, it might be wrong, but this is actually a really important point in this talk. Even though it's wrong, it is very interesting because clearly students try to get a smooth try to make this line touch the other line, which is already a very good idea. But also, these students had the pre-knowledge. They were able to compute the intersection points. So that's what we did. We let them compute the intersection points, and they found out, oops, we have 2. And this led to an interesting discussion, like, oh, if we have 2 intersection points, then that's not what we want. So the students came up with the idea that, we want 1 intersection point. So this is one way to think about touching, having a tangent line. That's when you have one intersection point. And then of course the teacher could pick it up and show an example where there would be another intersection a little bit further up with different graphs showing that, well, maybe it's not enough, but it's already a good idea. What I also gather from this is the 6.4 is a bit mysterious. What the students done is not just have one try, they must have tried different numbers. So they must have moved the line up vertically up to the point that it touches. So they've already tried varying this point. So what you could, for example, suggest is to put a parameter there instead of the 6.4. You could put a b, and then try to find when do I have exactly one intersection point. Trying to find out for which b do I have exactly one intersection point. And actually these students do have the background that they could do this computation. That was actually some sort of abstract exercise that they did before, and now it could be useful for something because they find one particular b for which it works. Okay, that's enough about this example. Let's look at another example. This is students who made a beautiful drawing of a parabola, and then they draw a line to fit to it as good as they can. And this is actually something they've learned at a physics class, they told me. This is how they learn if they have a distance time graph to determine the speed. So this is also pre-knowledge that they have, and that I was perhaps not so aware of. I knew it, but I never really used it in classroom, that particular. What was nice now, that it came from the students. They say, okay, we draw the line, then we pick 2 points, and we measure the horizontal distance and the vertical distance, and then we divide it, and then, you know, we have a slope. So they came up with this idea all by themselves. Well, not exactly. They took it from the physics lesson, but what was very nice is that they applied it here in this mathematical situation. I was extremely happy with this, even though if you look at how it goes on, it actually goes wrong, because they try to make the whole equation for the line and they mess up a bit. And I find this a very important lesson if you do an RME lesson, that students may come up with results that are wrong, but there may be very many good ideas in their things that happened before it went wrong. I could really use this. I asked the students to come in front of the classroom and present this result and show how far they got. And then, of course, I warned them a little bit where it went wrong, so they presented everything they did so far. And what what this task did for us is that it activated their pre-knowledge and their meaningful pre-knowledge and show how it applied in this course. And they also had a numerical way to produce the slope of the curve in a point. So it's excellent work, the students. Yet another observed approach is here. What I like about this one is also that there's a lot happening. These are all the same students and these are all different solutions. So the first one here, they use an exponential function, 1.5 to the power x. And this is really nice because, I don't think they know what an asymptote is, but they thought, that's more or less straight. And then they write, but it's not exactly straight, so we're not happy with this one. But somehow they already figured out that the steepness, the slope, goes towards being horizontal. So that is an insight. And then the next one is sort of trick solution. Here, they take half a parabola. It's inspired, I suppose, by the previous one. It's half a parabola, 5x squared. Y is 5x squared, to be precise. And then it meets just the positive x-axis. So it's again a nice solution. They realize that the top has a horizontal tangent line. Then they take it a different way. And this first one, I plotted it, I think, and it's really pretty wrong still. It has a clear intersection, it's not tangent, and they must have realized as well that they weren't pleased. So they tried something else. They didn't put the 0.3 x squared anymore. They went to x squared because I probably thought that was more easy. And then they moved on to half, so 1.5 x squared in the end. So they moved through several attempts and finally they end up, and this is a correct solution. I think I plotted it. Yeah, there you go. It's a beautiful tangent line. And so it's nice to see how they, in this case, Yeah, adjusted both the curve for the bended curve and the straight curve, and then in the end it was correct. So there was some development you could see here. Now this is also a very beautiful solution by the students. This is a group who had y is a half times x squared plus 2x plus 8 for the curved bit, and then y is 2x plus 8 for the line. And this is really beautiful because, of course, the connecting point here is in the origin. Well, not the origin itself, 0.8 is for x is 0. And they realized, sort of a general insight, that they could take the linear bit in the formula for the quadratic equation. They formulated it a little bit clumsily, saying the b in the formula of the parabola and the a in the formula of the line must be the same. But this is what they meant. And if you know about the Taylor series, then you see what they're actually doing. They're throwing away the quadratic bit. You don't really need to know about Taylor series X anyway. But what you do need to see is that they throw away the quadratic bit and they pick the linear approximation in the origin. So that's a wonderful idea, and they really invented that all by themselves. So this is a wonderful starting point for a teacher to start talking about linear approximation as a way to see the slope of a curve in a point. Now, and the final approach, which is yet again completely different, is this one. It's very algebraic, and it really fits with the pre-knowledge of the students. They did lots of algebra in the previous years, and they guessed a formula themselves, really. They said, okay, again, hyperbola 6 over x, and a line minus x plus 5. And as you can see here, is that they started solving it, and they found two solutions. And it's about midway in their workings here. They find x is 2 or x is 3, and then they say, oh, it's in Dutch. We don't want two solutions. We want one solution. And okay, I have to admit, these students are the clever ones. They are really good because somehow from thin air, they've decided that their equation should look like x minus the square root of x, the square root of 6 times x minus the square root of 6. Then they would have a double solution. So they found out how they wanted to change the equation that they had while solving, and they used that to change their equation for the line. So they changed the 5 there in a way so that they would have one solution to this equation. So this is sort of, I find this typical for the messy way, the way they can't really even explain themselves. Very clever students sometimes work. But so you have seen a variety of ways that students solve the task. And now, of course, the challenge for the teacher is what to do with all these solutions. So that's what we're going to talk about now. What should be your lesson structure for this sort of inquiry tasks? Now, first I want to just make a little advertisement for teaching in this sort of way, because there are benefits, but there are also problems. But let's first look at the benefits. The first one is, of course, the ownership. If you start from their own productions, students will feel ownership over their creations, and also, in the end, about the mathematical concept that you introduce. And as mentioned many times before, you're building on knowledge and methods that are meaningful to students. I'm not going to explain, I can tell you now already. So if these were results from my lessons, I'm not going to start off with introducing the derivative as a limit of delta x goes to 0, of delta I over delta y over delta x, because this has not come up in my students' works. So this, what students always find very difficult, is not going to be my starting point. I'm going to build on these methods that they came up with. But there are challenges. If you set a task like this to students, they will struggle and they will get stuck. And of course, this sort of work, this guided reinvention, this reinvention in inquiry has been also challenged by many people. some people say constructivist learning does not ask for constructivist teaching. That's the article here mentioned here. That's the constructivist teaching fallacy. But I don't believe it. I think you can do constructivist teaching in a good way, and I hope to present to you now how. But okay, students are going to get stuck. As was asked also in Paul Driver's lessons, there will be diverging approaches by students. Students will have all sorts of ways to solution, how to deal with that. And also they will have solutions that are not as good as the best solution or the solution you might hope for. So how to deal with that? Well, let me first say something about this struggle and stagnation, being stuck. So there are actually papers about this, and one very beautiful one here by Warschauer says that the struggle of students has the potential to be productive in mathematical classrooms. Well, we all know this. If you struggle with something, that helps, that's much better sometimes than just getting it presented in such an easy way that it doesn't provoke your thinking. So struggle of students has the potential to be productive, and even better, failure in task can lead to a deeper understanding than direct instruction. So here you go, trying to design this slide and actually not completely succeeding could lead to a deeper understanding in the end of what, for example, a derivative is, than if I just tell them what it is. Of course, this was not the context of this study by Kapur and Bilagic. Sorry, Polish people, I pronounced it the wrong way. But there are examples where it does, where failure in tasks lead to deeper understanding. I think you should allow your students to fail. And this is one of the challenges of actually teaching this scenario that I'm presenting now, but generally RME. Just let them not find the solution and still continue with your lesson. It's okay to have a few half solutions and take what comes from that. That's really contrary to what you usually want, because you set them a task and you set yourself as a goal to guide them towards the solution. So this is really a big step if you come from a traditional teaching. It was a big step for me too, and I still have to stop myself from helping the student towards the answer when I teach this sort of scenario. Okay, well, how to deal with the divergent scenarios? Actually, I was part of a project, the Erasmus Plus project named Myria, and well, apart from RME, we were also inspired in this project by the theory of didactical situations developed by Brousseau. And I'm not going to go at all into all the details of this because we've had enough theories for one day, I think. But for now, and also for our project, it was more or less enough to take this idea of building up a lesson. You introduce the problem, which they call the milieu, and you let students work on it. And now comes the point. While they work on it, you only observe what they do and you don't help them. You let them act, and you are reflecting and observing on what they're doing. Then you let students present their solutions. While they were in action, you looked at some of the solutions and you decided which one would be interesting to have presented for the whole classroom. So there you have, let's say, if they worked for 20 minutes, on the task, then you let them present and you take like 15 minutes to have 3 groups, each present for 5 minutes. Students can ask questions about this. What did you do? You can ask then, in the next stage, you're going to validate. And then you and the classroom may ask the students who presented, hey, is it true? Is it good what they did? What's useful from what they did? And you compare the approaches and you ask perhaps even the students, like, what would be, you think, the best approach? Or maybe how can we combine these approaches? And you take another 10, 15 minutes to do this discussion. So look at what happens in the time balance. They work about 20 minutes on the task, and now we've already spent half an hour on discussing what they did. So there's a lot of time for discussion, the results of their work. And then finally, then it's time for you as a teacher to do something important, because you have all these different approaches and these different ideas. And even though in the validation phase you may have already picked some ideas and try to merge them, now in this institutionalization phase you're going to try and put all these things together and connect them to your target knowledge. So if I have all these 5 different approaches from students that I just had, and I have to connect them to the notion of slope of a curve at a point, then, I would definitely go for the one that is the linear approximation. And I might show them how you can zoom in and say, okay, we have the line is an approximation of the curve, and this leads us to a notion of slope in something that's actually bended at that point. So I'm not exactly in that lesson, for example, even trying to make the bridge towards the official formal definition with limits. I'm very happy for that lesson, just to pick out such a thing and try to make it a little bit more formal, try to lift it out and put it there on the blackboard and show students, okay, so this is one way. Very happy also then perhaps to lift out this idea of having one intersection point and instead of multiple intersection point. And I might try to formalize that a little bit, that idea. So I pick 2 things, and then maybe the next lesson I would say, okay, these are our ideas, and at some point I will need to make the transition to the formal one, and I'll do that the next lesson. Okay, if you're interested in this scenario, there are even more scenarios. I just like to show you this one slide with the scenario that we made in the Myria project. If you just search for Myria project in Google, you'll find the webpage for this project, and you'll find more scenarios like this. So if you want to have material that you can start using in your secondary school, go there and look at the scenarios, and they'll look a bit like this. So they'll definitely tell you what the target knowledge is and what the broader goals are, prerequisites mathematical knowledge, and then what's not on this slide, then it will have much more extended description of what the lesson will be like, but you will recognize the 5 stages that I just presented in this previous slides. I hope you were able to ignore the terminology there, because that's not important. What's important is those 5 stages and what you do there. By the way, if there are questions now online, the problem is, unlike with Paul just now, is that I don't have anyone in the room here to keep track of the comments. So again, after this talk, I will have a look at it and I will very happily answer all the questions that are there. I'm really sorry that I can't answer them immediately right now. Then, where are we? We're making good progress. So what I've talked about so far is why we would have this task of the slide, how it should help students with meaning making, how the slide situation is a grounding situation. All pupils have experience with steepness and smoothness by going down the slide. All pupils have experience with handling equations for curves and lines. Now I bring these 2 together in this task, and that should provide a meaningful background for them to start reasoning about steepness in a mathematical way. Okay, so then we've looked at students' approaches, and you've seen that they actually really are capable of more than you might expect at first. I have to admit that I was doubting how far could they get. There's one thing I could say about that now, is that of course I had groups that struggled a bit with this task, and I noticed that students that are not so confident with the formula, they really like working in GeoGebra, because there you can put the formulas into any graphing software would work. You can put the formulas in and you can look at your results. Nice thing is, for example, that I had students there finding out how good it is to zooming and zooming in. Zooming in for me is the first step towards taking the limit, because you're changing the scale of what you're looking at. So that's a form of that's towards the process of limit taking. So that's again something as a teacher you could pick up in the last phase of your lesson. Let's have a few minutes to actually look at these different mathematical approaches of slope, because we're all familiar with the limit one, but there are some other ones. I try to look into this because I thought this is important. If students come up with something that is actually could be developed also into the notion of slope, but in a different way, I'd like to recognize it. So there we go. And I came with 4 different approaches that are, of course, related. I don't have time to go into the details, but I just want to show them right now. So the first one, so this drawing here should look familiar. We see all these different second lines, and they're moving, the point to the right is moving closer and closer to the other one. And the slope in the point is simply defined as the limit of delta x goes to 0 for f of x plus delta x minus fx 0 divided by delta x. This is the familiar one, but I would like to point out in all the lessons that I did for the study, never ever, strangely enough, well, I can explain, but never ever this came up. The reason is that students want a correct solution immediately. They don't want to have something that's wrong and then a little bit better and then a little bit better and then a little bit better. It has to be right. Although, as you saw, the idea is a little bit in one of the examples that I showed, but it's not really a continuous approximation. And they varied both the line and the curve, so it's really not comparable. Really, this idea of picking 2 points on the curve and using a second line doesn't come up because you have just 1 point, and it really doesn't make sense to them, I think, to pick another point. Then there's the locally linear approach, and this has been proven by David Toll to work well with students. This is something that comes naturally to them, and it came again naturally also from this slide task. Students do zoom in to try and see if their solution is okay or not. And this idea of linear approximation also came up with the students who threw away the quadratic term and went with the linear one. So this is clearly one that works and is worth addressing in classroom, I think. Then there are 2 more, and one of them has also been proven to work well with students. That's the algebraic multiplicities approach. It's the idea that we also talked about, that a tangent line is actually locally a bounding line. It's something that just touches in exactly 1 point. And why is this so nice for students? It's nice because this algebraic part, at least in the Netherlands, but I think in many countries, is addressed before they learn about derivatives. So they like to solve equations and so show how many solutions they have. Some have learned the quadratic formula to solve quadratic equations as well, and they know about discriminants, and when it's 0, there's exactly 1 solution. So this really is a nice, meaningful entrance to the notion of slope of a curve as well for students. And then I found this very obscure but beautiful, beautiful approach in a book by Marsden and Weinstein. And it's called the transition point approach, and it's sort of opposite to the limit approach, because what's the transition approach? That actually tries to make the idea that, okay, if I have a tangent line, then I don't have any, then I have just 1 intersection point. But if I wriggle it a little bit, a new intersection point will show up, either above the point or below the point. And they say it's sort of a transition. If there's this transition there of having 2 intersection points to 1 intersection point to 2 intersection points again, then then you're at the right tangent line, and then you have the slope of your curve. There's more to it than I can say now, but I can only promise you it's very beautiful. So if you have time to look into this approach, please do. Unfortunately, I thought students might come up with this idea because it's accessible if you look into it, but they didn't. I could not really connect their informal models to this more formal approach. All right, so we're almost there. There's just 1 thing left. I hope this was not too much information. Of course, I'll share these slides on the website, and because this is YouTube, you'll be able to go back in this presentation to any point you like and look at it again. But just to summarize, this was our one of our questions. Can students reinvent the slope of a curve at a point? This notion. Well, the answer is subtle, and the subtleties we've all seen them all in this talk, but I'd like to summarize them in this sentence. In this institutionalization phase, so the last phase where the student tries to, well, it says here, in the institutionalization phase, the teacher organizes the ideas and strategies presented by the students, the presentation was in the third phase, into a solution model of the slide problem. So there you have a solution model of this problem. The teacher makes a start with transforming this model of, this situational model of the situation produced by the students into the model for mathematical reasoning. It is very important for students to experience how their personal ideas contribute to the institutionalized model. In this way, they realize that they have a responsibility for the process of knowledge building. As a consequence, students' expectations may shift away from the idea that this is the teacher's responsibility exclusively. Now, I find this very, very beautiful, because sometimes, in the beginning when you meet a classroom, there can be this expectation of the students saying, you tell me how it works. They make you responsible of explaining how everything works. And what you want is students to take this responsibility themselves. And the only way this will work if you actually listen very carefully to your students and use their informal approaches. They may have mistakes, they may be wrong in some ways, but there will be useful aspects about as well. And to me, this is the heart of realistic mathematics education, that you use those ideas to make things meaningful for them. But more than that, the idea is that they also feel that they can contribute to the process of knowledge building, that they have a responsibility there. I helped us understand what the slope of a curve is. It was not just this man here in front of, woman, sorry, I'm a man, but this woman here in front of me telling me what it is, but I actually constructed it. It tells them a little bit that there may be hiccups in that process as well. I didn't give her the whole idea, but I contributed a little bit, and we did that together. And then we build up towards this more formal model of slope of a curve. So I think that's very beautiful. And I hope you're inspired by that too, and we'll try it. And that's another thing I wanted to say. Both you and your classroom will have to get used to this sort of teaching. I've tried this sometimes only once, and then students really had a hard time adjusting to this, to taking this responsibility. Some were even a bit angry, like, don't waste our time, just tell us how it works. And so you need give some time to, to find out together that this sort of teaching works. And also for yourself, it's not easy to teach in this way. But the very nice thing is that the third time that you try this in a classroom, students will recognize this, and by then they will have experienced how you use their ideas, and they will find this very motivating. So please try and give yourself some time. And I want to finish with just giving you this few references. So if you want to go a bit more in depth about these ideas, there are two papers on which I based this presentation. And the last one is really the most complete one, and it's open source, so it's free, available online. If you Google for this, I'm sure you'll just go straight to the PDF and have a look at it yourself. So I want to thank you for being here with me, for your interest. And now I'll finish this, and we'll be back online in like 5 to 10 minutes for the closing session of today. And a bit later today, I'll go back to this video, and we'll be very happy to answer your questions if there are any. Okay, thanks again for your attention, and see you soon.